Okay, it's great to see everyone here today. If you're like, please come up and grab pizza anytime during the talk for as long as.
Oh, then how did you come up with this? There's
Hi. Hello, Ron. How are you?
Good, how are you?
Good. Okay, so very quick survey before I actually get started. How many of you have heard about DeepSeek R1 before? Probably the answer is yes for most, right? So, okay. It's a good amount. Okay, actually, how many have not heard about it? Is this new and you're here for reading group for the first time? No? Okay. Cool. This is going to be fun. I'm very happy this exists because I love open source, and this is open source at least to the best of its own capacity. We will find out what the limits of that capacity are in the next hour, hopefully. But luckily, most of what we cover here today is relatively straightforward. It's not very rigorous. It's more an art than a science. But at least here they're showing us how to draw the painting, and not just giving us a photograph of the painting and charging us $200 a month for it. So yeah, before we actually get started with the material, a couple of things. If you are new to reading group, welcome. Please ask as many questions as possible. Do not hold questions until the end. It's easier if we have things in a more discussion-oriented format. I don't mind at all. Interrupt me as much as possible. Discussion is good, restating the obvious is good, more clarity for everyone so nothing is lost. And I will probably get some things wrong. This paper was released January 23 something, it is January 30th, so we have less time, but that's okay. It just means I don't have everything exactly perfect. Hopefully though, if you find something doesn't make sense, let me know and we can try figuring it out together. I have the actual paper as well. So there is that. Okay, before we get started, any more questions? No? Yes? Okay. Fantastic. The overall process that we cover today is to talk about reinforcement learning, because that is at the heart of the DeepSeek R1's result. And then after that we'll discuss some more training details. There is no math after section 1. And section 3 is purely empirical. There is not too much to discuss there, except we can say, oh wow, the number is very high, right? Cool. So, reinforcement learning review. Proximal policy optimization. This is the standard process that is used for training any reinforcement learning based model, at least in the modern era. And for LLMs specifically, they almost objectively always use PPO in combination with DPO if they're feeling fancy. But the overall idea behind reinforcement learning is you are given a reward. This is in the form of a function basically, where you assess the performance of your model and give it an objective score. This is usually by itself not differentiable, which is why you cannot directly compute the gradient with respect to the reward and update your model's parameters that way. So reinforcement learning basically just tries to get around that problem, and proximal policy optimization is one of the ways you get around that problem. So let's start by talking about what all of these variables mean. The two terms that are there, right? It's just one thing that multiplies with the second. We are taking expectation over the questions, and PQ is like a probability of a question appearing. So in the standard case, usually it will just be selected uniformly at random. But if you have different types of data, for example, programming languages, you have Java and you have Python, and you have a lot more training data in Python than Java, you can probably reweight it, and that will sample from the data set accordingly. O is sampled from pi theta old. Pi theta old is your starting, is the model parameters before the update. Pi is referred to the policy, that's just the reinforcement learning, that's just the LLM in our case. Outputs are sampled from the set of from the model itself. So you randomly, not randomly, you are sampling from the LLM. If you are performing a greedy search, it is going to be consistent, so you can sample multiple times and get the exact same answer. In practice, that's not always done, where you will extract or select a token that has less than the highest predicted probability. And in that case, you have some degree of randomness associated with it, which is why we are actually sampling from the model itself. Then, from there, the second part of this term is the clipped surrogate objective, which is basically us comparing the likelihood of the change of the old parameters to the new proposed parameters times an advantage function, and we are basically taking the minimum of that same computation versus a epsilon delta clipped variant of the change. Okay. Now it looks very complicated, but the general idea behind proximal policy optimization is you want to take small steps towards your actual target, right? You don't want to jump, because fundamentally reinforcement learning is very unstable. If you take steps that are too big, what is going to happen is that you will have your model basically irrecoverably get some low amount of reward, and it will never basically recover from that. So the idea is you take small steps, and if you have a very small learning rate, that gives you another problem. You're going to have very slow convergence. So proximal policy optimization says, hey, here's what we're going to do. We find a decent middle ground where the change of the new parameters has to be within some epsilon gap of the old parameters. And if the ratio of this policy changes drastically, right, not the actual, like the W norm of the parameters themselves, but the ratio of what the predicted tokens should be, if that changes drastically, then we want to basically restrict that, which is where the clip comes in, and the clip objective basically restricts the size of the steps that you end up taking. So if it is smaller than that, very good, no need to worry, otherwise you would select the clipped objective. The output of pi usually is a distribution, and what that means is basically if I have 3,000 or 30,000 tokens in my vocabulary, right? It can pick any one of the 30,000 words as its prediction, and that once you run softmax on it, you will have one set of tokens that have really high probability of being the next token, and most others that are like very long tailed. So you will have one specific token that is really high probability, some of them that are similar words semantically, but still lower than the mode, and then other words that just don't make sense given the context. And sampling with very low temperature basically means always selecting the mode, but sampling with high temperature means that you are more likely to select some of the tokens that are far away from the mode. So higher temperature means your prediction is going to be more random, which is good in some cases because you want to generate, for example, multiple stories and not the same exact story every single time. But if you overdo it, you're going to get random words too, which doesn't really make sense. I see a question?
Temperature actually sort of like flattens the curve, makes it more even. It doesn't really change how you sample.
Oh, yeah. But you still have to sample with some degree of randomness, right?
Yeah,
so
you have to sample, but it like changes the curve to like make it more towards your.
Okay, I see. So, wait, let me see if I get this right. Yeah, if I have higher temperature, it is going to be like this.
Yeah.
And
so the tails will be higher.
Tails will be higher. Yeah, and but when the actual sampling procedure, is it how like some standard?
It's still just softmax. Temperature is just included inside you.
Right. No, I guess my question is, am I still sampling the mode? Because the mode will not change, right?
I mean, you're always sampling, unless you're just doing greedy search.
Yeah. So no temperature is just greedy search. High temperature, you're more likely to select tokens that are not the maximum, right?
No, it's like it's like that. Whether or not you want to use like beam search or something like that.
Okay. All right. Well, I guess high level ideas remains the same. I'll look into the specifics later. I apologize for that. So cool. The idea is you will get more randomness in your prediction. And yes, okay. The thing that I have not actually spoken about is this A sub I term, right? Because we are comparing the change of the parameters or the change of the policy given our new parameters theta. But what is a sub I? That generally varies a lot, but the paper that DeepSeek talks about is this paper called Generalized Advantage Estimator, which has one advantage of estimating long trajectory rewards. So if I'm yes?
I'm sorry, before you continue, I just wanted to ask what does temperature mean then?
Okay, let's see. The idea behind softmax is you are performing normalization, right? So I have a vector of tokens. So let's say the tokens are like a vector of logits, sorry, not tokens, and let the logit values be 1, 0, 3, and 4. Okay. Now this itself is real valued. It could be negative infinity theoretically. It could be positive infinity theoretically. And I want to convert this into a probability distribution. So
Yeah, we can see. We can see. No, like the camera's blurred. Oh, no.
Thank you.
yeah. Okay. So you have these values. These are logit values, and each of these corresponds to a specific token. So if I have 4 words in this case, right? You are basically trying to convert this thing into a probability distribution, and it needs to have 2 properties. Each value has to be greater than or equal to 0, and all of the values need to sum up to 1. So one approach for doing that is softmax, where you will take the softmax, where you would do for a specific character, take e to the value x and then sum up over e to all of the x's in the logit vector. So let's say this is y hat, x and y hat, e to the power x, and then this is for a specific token or a specific class, because technically it is just classification task, right? So here we basically sum up e to the power all of these logit values and then divide it by the actual target value, and this will convert it into the policy. Now my understanding of temperature is, I think maybe correct me if I am wrong, but you would add something.
No, you divide. Adding won't change anything.
Divide
Divide by t.
Divide by t. Okay, cool. So divide by t, and that makes it more uniform. So instead of the tokens, for example, right, this is not mathematically accurate. I'm guessing this will be 0.7. Oh no, that doesn't sound right. 0.6, 0.3, 0.01, and you're left with 0.09, right? Yeah, okay. Something like that, right? And then this, if you increase the temperature to be very, very high, it will be close to 0.25, 0.25, 0.25. And then how do you know which one you want to select, right? That is the part that temperature plays when we are actually computing the predicted probabilities. And now basically given this probability distribution, you have to figure out which token to select for the next word. If these two are really close to each other, you can probably say, let's pick this one instead of this one. And I'm not sure what the rule is for that specifically. Greedy search, which is what we were talking about, is always just pick the maximum one. And that, unless your temperature is basically infinity, it will always be the token which is the mode, right? And that won't change by temp.
So actually, lower temperature means less random. So at infinite temperature, right, everything goes to 0. And
Yeah, it will fully. Yeah,
so
exactly.
At 0 temperature, you're spiking.
Yes.
Yeah.
No, wait.
So lower temperature means more. Lower temperature means more deterministic.
Yeah. So as long as wait, did I misspeak?
Yeah, it's.
Okay, sorry. Okay, cool.
Wait, but what's the technical definition of temperature?
It is literally that value t that you divide by.
Okay, cool. Sweet. Yep. The downside of PPO is that it requires a neural reward model, which is expensive to train and can also be unstable. Usually the reward model for LLM specifically is the same size as the actual LLM that we are attempting to fine tune. The only thing we change is the final layer, which instead of being like classification over the 30,000 tokens, that is your vocabulary, it's just a single real value. And that's, I guess, what we're going to talk about next. But the problem that comes as a result of that is that it is just very, very expensive, right? So RLHF specifically uses proximal policy optimization in order to fine-tune a model. This is again mostly review where RLHF will still be used for DeepSeek, but the main thing that changes is PPO, not RLHF. Or I guess the knock-on effect is RLHF also changes, but we will get to that very soon. Question?
What does HF mean?
Reinforcement learning from human feedback. So the humans decide which response makes most sense, and then on the basis of that, you will fine-tune your model to basically move it towards whatever the humans prefer. Question? Yeah.
Is it the same as when the ChatGPT asks you which response is better? Is that RLHF or is it different?
I don't use ChatGPT. I'm not familiar with the interface. But Alexi's nodding yes, so I'm guessing yeah. Okay. Cool. More questions? All right. So the RLHF pipeline, this is one way of doing it. Zeiger et al. Published this approach, and I think it makes the most sense. Generally, I think it works well for like a one-size-fits-all solution when we're talking about RLHF. But there are variants you will see across the board. The first step is supervised fine-tuning, where you have a pre-trained LLM that is fine-tuned on high-quality domain-specific data sets. So if you are trying to perform reasoning tasks, you would probably find a reasoning data set and just run supervised fine-tuning on it. And this is the step that DeepSeek skips. Basically, they say it is too expensive, and we just will directly do reinforcement learning, and it will work. The next thing is reward modeling, where we model users' preferences. So you have a data set where you have one response that is preferred over the other when you sample from the supervised fine-tuned data set or supervised fine-tuned policy, and the human decides which word is preferred over the other, and that is basically a virtual R star. This R star is unknown, which we are going to approximate using a language model, or language model with the head replaced with a final real valued output. So Brady Terry basically just uses a softmax to convert the preference of one over the other into a probability distribution. This is I guess just the same continuation of this formula. This is the preference distribution optimized over negative log likelihood over your parameterized model. The additional notes, I think, not super relevant for DeepSeek specifically, but for RLHF, yes. The rewards are normalized in order to motivate lower variance. Otherwise, it is too spiked, and then that motivates more collapse, where instead of learning to maximize the reward, it will give you word soup that will make the reward look good, but it will not actually satisfy the underlying task. R5 is PySFT with the final linear layer that returns the scalar reward. So that is what I was talking about when you have the same language model under the hood, but you just replace the final layer in order to obtain a reward model, and then you fine tune the parameterized reward as well. Question?
So lines 2 and 3 are basically creating a preference data set where you sample the model with input X, you generate Y1, Y2, and then line 3, you then R star is like the human preference where you ask the human, you give it X and Y, you give it X and 2 Ys, and you're basically asking the human to rate which response is better.
Yeah.
Right? So then what's the line 4 then? What's like the greater, like this arrow? Is that like just greater than, is that like preference?
Yeah, that's just preference.
Okay. So then you...
Oh, the probability of that preference. It's just conversion into a probability.
Okay.
Because we have preference which is objective, but we are not saying how much do I prefer this, right? So just to give it a little bit more numerical stability, you convert it to a probability distribution, and that is just done by performing softmax over Y1. I think should correspond to the winning prediction, but that will just
To the what? To the winning? Like YW is Y1?
I think it should not really matter because it's still the if
right,
it is the
right.
loser, it was still it's just they both add up to one. It's one minus the other.
Okay.
So in the actual RLHF process, I get that you're performing softmax over the two predictions, right? But how do I actually, I have this parameterized model of R feed. How do I actually update that given one of those like binary results? Do I understand that?
Yeah, that's standard backbone. You obtain the actual reward value that you expect through this process over the preferences,
Yeah.
right? And then you have the prediction that you wanted to get. So it's not 0-1, but it is yeah. It's not learning the one-hot encoding for what the winning value is. We want a okay, yeah, no wait. So Alex, you are right. This is not y1 is the winning one only because we want a real value.
Okay.
So we're converting the prediction of the winner to the real value by obtaining only the winning logic,
Gotcha.
and the winning logic is converted into the whatever the probability value is, and we want the reward model to predict that exact reward or the reward that it should be assigning for that prediction. So that is the idea. And yeah, that is the preference distribution. Supervised question.
So the reward model is primarily based on feedback. That's it. It doesn't factor the latency and anything else.
Does it factor?
Like time things. It's just.
Oh no, it's just the prediction. But the response, at least for traditional LLMs, should be consistent regardless of the variance between predictions. Provided length is the same, it should be relatively static. Like there will be random minute differences, but I don't think practically it is relevant.
Could you talk a little bit more generally about why DeepSeek is the first one to figure out that we do this, like not supervised learning? Like how does the reward model do? Because if it's just rewards based on supervised, it just seems similar to the supervised. You want to talk about it?
Oh, it is in fact supervised learning only. We are training this reward model using supervised fine tuning. But the important difference is that instead of we have our original policy. Is it clear? Yeah. We have our original policy that will give me the 30,000 valued vector, right, as the final result. And now I basically don't want this because it will say what is the most likely token, right? When I want reward, I want a single scalar value that determines how good this prediction by this specific model is. So this R phi will take in the inputs, which is just your standard set of tokens. Wait, is it? Yeah, and then predict a reward on the basis of that. So this is just a single scalar value. And the target, right, what we want the optimal value to be is determined by equation 4. And then we are simply learning that value itself. So I don't know exactly what loss is used. My guess would be mean square error is the most obvious. But it's just normal gradient descent to approximate as closely as possible those values. And now you will have, if everything is ideal, right, R phi is a model that given an input will tell you how good that input is, and you can then use that as your reward and have the reinforcement learning model actively produce outputs that maximize said reward without outputting gibberish. So that will be next slide. But does that answer the question? Okay. For sure, no clarification, right? Okay.
I was just curious because like the first ones, it seems sort of intuitive. I was wondering, the first ones to sort of apply this logic to an LLM that's like really comparable to the current ones that we have. So.
Okay. So can you repeat that one more time, please?
Yeah, that's fine. You can go on.
Okay. Okay. Cool. All right. R fine tuning. We use R phi to fine tune the supervised fine tune model, which has the following objectives. We want R phi to be high because if we don't have high reward, what's the point? The assumption is that R phi actively models R star or is a close enough approximation. but it allows us to generalize beyond just the preference data set itself, because it is unlikely that our model is always going to output things that are covered within the preference data set that we have collected. We don't want mode collapse, which is random tokens that will maximize reward. That is reward hacking, basically, where we are not achieving the original objective we set out to achieve, but just because it kind of cheats the R5 that we have trained, it seems to like that result, but obviously that is objectively bad. The solution for this is to add a KL divergence penalty term that minimizes the divergence from the original supervised fine-tuned model. So we are positing this optimization problem where we want to maximize the reward while keeping the divergence from the original policy to a minimum. So it is saying that we still want it to speak reasonable English, right? Assuming this LLM is trained over English, and we want it to also satisfy the objective of being helpful. In DeepSeek's case, it is censoring against the Tiananmen Square massacre or whatever. But they're going to use this in order to make this model perform certain changes or some minute tweaks to the actual policy, and provided that is satisfied, it is good. If we set this beta parameter over here is like a hyperparameter. So if beta is equal to 0, you don't care about divergence at all, and it is free to do mode collapse. If it is very high, any change from the original model will be penalized very heavily, so you won't really get the maximization of your reward, although it will still be as close to the original model as possible. So cool. This is equivalent to the following reward function, which we maximize using PPO, which we discussed earlier. Now, the main error or the main problem with this setup, right, is we need R5. R5 is expensive, and China does not have H100s or does not have H100s that they're publicly allowed to disclose. So they have to basically work around that. And in this case, they came up with GRPO, which this is not part of the DeepSeek R1 paper. This is part of, I think, DeepSeek Math. But the basic idea is, instead of extracting a single sample, obtaining a reward over the sample, you extract a bunch of samples from the previous iteration or the previous set of parameters, and then this bit remains consistent, right, with PPO. But the difference over here is now we have just this formulation of A sub I, where A sub I is literally just the z-score of the reward. So that, and then they also modify the definition of KL divergence slightly. I tried to figure out why that is the case, but I could not really figure that out. But yeah, the new objective compared to PPO, if we compare and contrast very quickly, right? We had a single O that was sampled from pi theta old. Now we have a set of them G, and then in order to compute the advantage, right, which is A sub I, we compare R sub I minus R bar over just the standard deviation, which is z-score. Okay, now up to here we have defined everything except for our reward function, right? We defined how to compute the optimization objective, but we don't know how to define reward, and the way they go about it is actually very vague. So the paper talks about the reward function or the reward model being rules based. So this is a reasoning task. You have a reasoning data set, you have a math data set, and you are supposed to give answers to mathematical questions or solve some programming challenge, right? And the way we define how well a mathematical question was solved is, did you get the right answer or not? And for programming questions, did it pass all of the unit tests or not? And the way that they go about this is also just that. They say, if you correctly answer the question, you get a reward. The other reward that they specify is if you follow the required format, which is putting everything in the think brackets, that is like the reasoning steps, and everything that is the answer itself an answer, you get a positive reward for that. It is very, very, very basic, right? There is nothing insane about this. The problem, at least my personal vendetta with this, is that they don't specify a function for obtaining the actual reward itself. I found someone who tried to reproduce the aha moment of the paper, which we'll get to in a second. But basically what they did was they just specified 0, 1 reward. If you get the correct answer, you get a 1. If it's a wrong answer, it's a 0. If the format is met, you get 1. If it is not met, you get 0. I am surprised personally that this worked at all because it feels too binary to make sense, especially for reasoning tasks. But I guess that is part of the magic. The overall difference, if you compare with the graph form, it's the same thing that is just a little bit more easy to see visually. The value model that was there from earlier is no longer there. Instead of sampling a single output, we are sampling a group of outputs. Then instead of performing the generalized, I forget what the full form was, we are just performing that z-score computation to obtain the advantage, and then the standard optimization goes where you calculate the policy gradient, rate parameters, and then whole process keeps going until you converge, until the model converges. So that is GRPO. Question?
Yeah. So the way you stated the rewards, for example, like enclosing in the think brackets and all that, does that imply that like A1 through AG is a sequence of like continuous tokens from?
No. A1 through AG is a sequence of answers. So A1 is one
it's a
answer.
sequence of whole entire answers. Okay.
Yes, each A is, or like each output O1 through OG is the set of answers. So we are sampling the for the same question we are sampling multiple answers. PPO case you only sample one answer, so one response, but it is one full sequence of tokens, one full process of reasoning.
Okay.
Awesome. Do you have more questions? Okay, cool. So that ends the mathematical part. So it should be much more relatively straightforward to follow the rest of it, or definitely easier for me to explain it. So the training process can largely be broken down into 3 stages. First, reinforcement learning directly on a base model. So there was the SFT step in RLHF where you find a domain relevant data set and then train this model that knows English well, but now specifically also has some degree of knowledge or understanding about a specific topic. And this will get us DeepSeek R10, which is one model. The next is reinforcement learning plus supervised fine-tuning on a checkpoint that is obtained from R10. Question?
Yeah, so for the R10, do you start with like 0 initialized weights, or do you already have like some like pre-trained model?
Yeah, you have a pre-trained base model. So you have modeled the English language correctly, but you don't have any specific domain-specific information. So in the normal RLHF setting, right, you will start by with a base model, and then you will create a supervised fine-tuned model, and then use that in order to sample answers and then do reinforcement learning with human feedback. But in this case, we are just starting with the base model directly. Alright, cool. Reinforcement learning plus supervised fine-tuning on a checkpoint. Again, these are vague intentionally. We will get into the detail, but it's just to give you all like an outline of what we aim to cover or what we're going to get. DeepSeek R1 is the main model that everyone has been talking about, and then after that they also managed to distill a couple of open source models, and then that is named DeepSeek R1 distilled and whatever model they named. Questions over that?
Yeah, what is the base model composed of?
The base model is in the architecture.
DeepSeek, yeah.
Oh, okay. So they use a couple of things. It is the base model is DeepSeek V3, right? And the thing they covered was, or like the general architecture was mixture of experts, and for the attention layers, they had multi-headed latent attention. And before each of the attention blocks themselves, before the attention and the MLP layer within the transform block, they also had RMS norm. So that's, I guess, the high level of the architecture, but I think not getting into that was an intentional detail. But if you want the DeepSeek V3 would be the paper to check out, because this is basically just a fine-tuned DeepSeek V3. Alexia, any
I
question?
don't see any details about the base model. Like,
It's a different paper. It's entirely a different paper. It's DeepSeek V3. I can pull it up. 1 second.
I'm sure it's not ChatGPT 01.
This is the architecture. So this they train on just English, right, or English and Chinese, and then after that you want to fine tune this model for reasoning. So this is our starting point. But then there are again additional complexities associated. One second, let's see. There are additional complexities associated with discussing mixture of experts and multi-related attention, which is why I didn't explicitly mention that. Yes.
Yeah. Okay, sorry. At a high level, do you know what the difference between regular attention and latent attention is?
They discussed this over
Just
here.
at a high, if you don't know, no worries. I was just curious.
This is the overall scheme, but basically I think they are using the part of the idea behind MHLA is they are trying to speed up the process of inference by using some compressed latents over which they are actually processing attention. So it is the high level, very abstract idea. The exact details are included down here, but yeah, exactly, I don't know. It uses rope, which is what you discussed last time.
I think they just do an encoder and intention over latents after that.
Yeah.
And then do a decode to bring back up.
Okay, cool. One other thing, this is something that was not discussed in the paper itself, which is something I picked up from reading it, was this connection to this paper called Lima. Less is more for alignment. It is a very interesting paper, but the primary insight from it is that you want to use a small set of synthetic examples to fine-tune your data set, and that encourages better generalization. Data sets obtained in the wild generally tend to be noisier, and a consequence of that is you suffer from learning spurious correlations a lot. And their synthetic data, which consists of very carefully selected samples, basically motivated better learning as a consequence of the controlled randomness. So the overall idea is that less or controlled randomness and having unbiased initialization in an unstable regime can help avoid falling into local optima and complete failures of training where you get to a low reward and you are unable to recover from it. Reinforcement learning is inherently unstable, which is part of the problem with the approach that they have taken, and a lot of what they discuss are mitigations to make the paradigm actually work. So this is strongly exemplified in the approaches that were used. Firstly, we don't need a neural reward function because we don't want to deal with the problem of reward hacking, where the model kept trying to, or where the actual model that we were trying to obtain just kept trying to break the reward model and find something where it would spuriously award the very, very, very high rewards, and it created this sort of balancing act. We don't want that, so let's skip it. The other thing is no need for supervised fine-tuning. Let GRPO figure out the best approach from scratch. And this again is a hypothesis from mine, but I think that the process of supervised fine-tuning pigeonholes the model into finding a chain of reasoning that is direct, where you go from the question to the answer in a very linear fashion. When you're trying to work out homework for a tough math class, right? A lot of the times you will try an approach and you will say, oh, this completely fails, tear out the paper and start from scratch. And I think part of the problem with supervised fine-tuning was it motivated this setting where you always end up at the right answer at the end of your thought process. and as a consequence, it pigeonholed it into a local optima and also led to a lot of hallucination where it doesn't learn to backtrack its thought process as effectively. So, starting with just a general base model and letting GRPO figure it out ended up being very significant in terms of improved reasoning as well. The other thing, no need for a complex prompt. Don't bias reinforcement learning towards the type of approach. So, say every step or try and rethink your solution and provide some verification. Too much overhead, biasing the model towards the solution, we don't want it. The prompt that they ended up using was very straightforward. How good is this? Yeah, so that's it. A conversation between user and assistant, asks a question, assistant solves it, the assistant thinks about it and provides the user with the answer, and it is in the thought process is included within think, the answer is included within answer, user, that's that prompt is replaced with the actual question, assistant, and then the answer is the sampled set of tokens, right? So that's the entire prompt that they used. They didn't show a bunch of set of samples or examples for it to learn from. It just by default said figure it out from here. So this combined with very carefully selected data were key to the incredible performance on the benchmarks. So reinforcement learning on a base model, you would start by taking a base model, no supervised fine tuning, but it models just the language well, and you train with RL until convergence of the task. Note they didn't ask the model to use a long sequence of tokens or try and figure it out using many words, right? It just said figure out the correct answer. And over time, if they found that the approach by itself learned to use more tokens in order to think more and get better responses. In addition, it also learned to think anthropomorphically, which should be somewhere over here. Aha moment. Yeah, here. How is this? Okay, so as part of the thought process, right, the thing in red, basically what ended up happening was the model was able to figure out at some point that it is making a mistake or it needs to recheck its work and maybe try a different approach. And doing that was something that just was emergent, right? This did not come as a consequence of fine-tuning or forcing it to think in a certain way. It just basically figured it out. So that was something that was really cool, and they did manage to achieve very good benchmark performances on this as well. Yes, question. Sorry.
I was wondering what convergence on task means.
Just wait. There is a graph here. Right here. It just stops. You just stop obtaining improvement after a certain period of time. So it converges at the end there. That's the best it is going to realistically get. So once you reach convergence, you stop training. A period of diminishing return, basically. Sweet. More questions?
Does that mean that it kind of evolved reflection on its own?
Yes, exactly. It figured out to reflect on the on the given question and the approach that it was taking by itself. Where I lose it? Yeah. So it figures out that hey, there is something that I can do here, and it figures that out completely without prompting from the user side. So that is something that was really cool, and I think this is probably the key result that they discuss from this paper itself. That you don't need supervised fine tuning; you can just directly start, and everything seems to work out by itself. Okay, so there were a couple of negative consequences from this approach. The first one is poor readability because the base model was trained to be multimodal, multilingual. It reasoned in a combination of English and Chinese. And if you don't know English and Chinese, then it is difficult for you to follow the thought process of the model. So there is no reward that is motivating readability, and there is also language mixing. Readability, I guess it was a separate issue then, where it just did not have linguistically accurate reasoning tokens, but it did help it solve the problem. So that was something that they also had to figure out. So getting the right answer is not always enough. It is always also helpful to figure out the procedure, because as a user, it helps you understand what's going wrong and how to fix it, or I guess prompt or converse with it to get it on the right track. So these are important things for reasoning models. And they did figure out the second part for R1, where it should be fairly easy to implement a reward for consistency of language, where the proportion of tokens is basically the reward. If the question is in Chinese, the proportion of response tokens or reasoning tokens that are in Chinese becomes the reward. But the consequence of that is that performance degraded slightly. So I'm bilingual. I speak both English and Hindi. A lot of times I think about things in that mixture of languages. So intuitively, I guess there is some logic to why the performance degraded, but these things don't always work intuitively. So it's a guess at best. Now, solution to the first two challenges, right? We have or we want better readability, and we do not want the mixing of languages when it is attempting to reason and respond. So they solved that by reincorporating supervised fine-tuning, but very, very briefly. So you collect data for like long chain of thought sequences, and for a very short period of time you train it over the or not for a short period of time, but few epochs, or for a very small data set you train it to approach problems in a more human-like way, and then reinforcement learning just starts from there. Traditionally, reinforcement learning finds a solution that is close to the original, and we still do retain the term in GRPO. I see a question over there. Yeah.
Did they test comparing between? Sorry.
What slide?
Yes. It was when you were introducing that. This one. Did they test the model between no language mixing and language mixing?
No language mixing and explicit language mixing did reduce the performance. Yeah, so they did test it, but it was shown that language mixing degraded performance. They said slightly, but it did degrade performance.
I just didn't know they actually tested it.
I did read it. I don't remember where though. Yeah, I'm pretty sure that was the case, but I can check and let you know. Awesome. Yeah, GRPO still motivates keeping a similar answer, because we still retain the divergence term. So it traditionally is going to get you an answer that is close to the initialization, which is part of the reason why supervised fine-tuning was done in the first place. So the idea is to use cold start to help it think about problems that are in a readable way and without any language mixing. And once that was done, a closed solution to that ended up being the actual reasoning model, and that ended up being the actual R1. So what is cold start? Collect a small amount of long chain of thought data to fine-tune the base model and make that the initial actor, and then expect a local optima to find a solution that leverages the readability, so better readability within the long chain of thought that was the original data that was used for cold start, and prevents language mixing. How do you actually collect the data? They used a couple of approaches. First was few shot prompting using a long chain of thought as examples. They queried DeepSeek v3 for this almost entirely, basically. Prompting with specific constraints, so you ask for a detailed explanation along with a reflection as well as a verification. And then manually, they also took a couple of DeepSeek R10, not D3, sorry, DeepSeek R10's outputs, to remove things like language mixing, fixing readability, and just generally refining the response. So they collected a small amount of data via cold start question.
Yeah, so in your previous slide you mentioned about problem with the zero model, not having proper readability.
Yeah.
And the way, what you have explained is no rewards motivating readability.
Yes.
So this could have been simply fixed in the RL stage if the reward model, apart from including the accuracy and format reward, also had a readability reward.
Yeah.
So why use it
The thing is, it is difficult to model it in a stable way, right? So the idea being traditional RLHF is I will have this parameterized reward that is going to be the amalgamation of all of the rewards that we, or all of the things that we want to parameterize, right? So readable answers, no language mixing, getting the correct answer, and having the correct format should all be expressed by this parameterized model R5. Readability is something that is a lot more subjective, right? It is hard for us to assign a score for it in just a direct mathematical formulation. And we don't want to use policy models, or sorry, not policy models, reward models, and like neural reward models, because the neural reward model is very unstable. So it's basically more trouble than it is worth. And their idea is, if it is going to find a closed solution anyways, let us basically give it a prior of readability and no language mixing, and then just let reinforcement learning run. And that should give us a good balance between the two.
Yeah, but like why not fix it in the first attempt and why fix it later? And if you are fixing it later, it means you have a different reward in the first stage and a different reward set in the next stage.
So the reward doesn't change. They fine tune the base model with cold start data, and then or not. Yeah, they fine tune the base model in this case. Yeah.
R10 model.
Wait, let me recall correctly. One thing that I also did find confusing was R10 is with direct RL. They restarted training with the zero model, not with zero, with the V3 model, not with the zero model for direct SFT later on. So it does get a little bit confusing, but I think for this case, cold start still basically is the same, right? Where we get for R1, it's basically cold start over chain of thought data, and then the same reward modeling process. I don't know. I don't think there is a very reasonable way of motivating readability, right? The one guess would be approximating by like binomial statistics. If there are words that are not very commonly together, I would assume that's poor readability. But it's just easier to skip it and then add that as a prior and then only maximize for the reasoning specific tasks. Sweet. Cold start, collect data, and then rejection sampling and supervised fine tuning. So this is where we end up restarting from V3. Once RL converges, you use the training checkpoint from the cold start reinforcement learning model to sample from itself as well as domains beyond just reasoning. So creative writing, role playing, as well as other general purpose tasks. And the idea is basically we will use this to create a new distilled set or a new distilled data set, and then run supervised fine tuning again on zero based on the outputs that you have gotten from the reward policy, and it ends up working well. So we basically go through this entire process again with the zero with cold start model and start to extract a series of tokens that are relevant. So we have, I think, 600,000 tokens or samples from that are reasoning based, and then an additional 200,000 that are not reasoning based. And this new data set that they get that they obtain from sampling from a checkpoint that has converged gives us the final reasoning model. So besides that, they also incorporate a generative reward model with DeepSeek v3, and this is contradictory to what they said, where a reward model ended up being bad for reinforcement learning. But the way that they are going about this is they are using DeepSeek v3 in order to perform data processing. So it is automated data processing by another language model to remove outputs that it thinks are not readable. It is not part of the original reward modeling process, which is why we don't have to worry about stability. It is part of the data processing pipeline. Question?
Yeah, so when you said they retrained like another model, is that other model is based on the first model's like output data?
Yes, exactly.
So couldn't they do that again with this model? So did they have multiple steps of retraining, or was it just?
It was, they started off with 0, did reinforcement learning, found out there is a problem, did cold start with reinforcement learning. After that, they used that model as a data generation model, made a new data set, and then used supervised fine tuning on that. And they could do it iteratively. That is the principle behind weak to strong generalization, right? Where you take a weak model, sample the outputs, see what works best, and then make the resultant model better as a consequence of that. But I think they only did one round of this whole dance. Okay. Sweet. More questions? Alright, awesome. Okay. Next, they're sampling multiple responses, retain correct ones. That is just rejection sampling, and we get 600,000 reasoning related training samples from this. Next, another 200,000 tokens for tasks like factual question answering, self-cognition, and translation. This was data that they extracted from DeepSeek v3's training data, and they are again training it on DeepSeek. They are still training on DeepSeek v3, and this is a hint towards the catastrophic forgetting that we will encounter later on, where which is one of the drawbacks of this approach. We'll discuss that in a second. I guess I'm getting a bit too ahead of myself, but keeping this on topic, we have additional set of tokens that are not reasoning specific, but still the majority of the data set is for reasoning, and that basically concludes the entire data set itself. For the 200,000 tokens or samples, maybe it should be samples, right? Give me 1 second, sorry. Let me be correct here. Yeah, samples. It should be samples, not tokens. So 600,000 reasoning related samples and 200,000 reasoning related samples. Not reasoning related samples. Okay, and for the non-reasoning related samples, chain of thought is not something that is actually present within the sample itself. Wherever it was relevant, they just asked DeepSeek v3 to generate a sequence of reasoning, did partial human validation to make sure that everything makes sense, and then sent it for training. So then they run supervised fine-tuning over DeepSeek v3 base for 2 epochs over this data set, and that becomes the final R1 model. So reinforcement learning was still a very critical part of this, but the final model that we obtain at the end is just supervised fine-tune over the base over this new data set that we have curated. And that is where the careful curation part comes in. Reinforcement learning is extremely relevant for data set curation, not the ultimate model, which is something that is confusing to think about, but that's the whole approach kind of summarized. Sweet. Questions at this point? Rohan?
Can you talk about how the SFT data is like curated or generated? How rejection sampling comes into it?
Rejection sampling is you just sample a bunch of answers. Human validator determines if the answer is correct or not. So you will get the correct answer after a lot of sampling, provided the policy is approximately where you want it to be, right, but not precisely so. So you would sample over time, you would obtain one result which is the actual correct answer, and you will select that for the data set. Everything else you discard.
But how is the SFT data set like sampled on what basis is it sampled from the?
Sorry, I'm not following.
How is the SFT data made?
This whole
Comes
process
from
is
the model, right? It does not come from outside. It comes from the model.
Yes. So you use reinforcement learning to train the reasoning model, but the reasoning model has issues where performance is still not exactly perfect. Readability is partially a concern, and language mixing is partially a concern. It has been mitigated to an extent, but still, even with the new approach, we just expect it to be approximately there. For it to be precisely there, we are using this new reinforcement learning model as a data set generator, where we are sampling for the set of questions and trying to identify which of the samples actually has the correct answer. You pick the sample that has the correct answer and add it to the data set. Keep doing that for all of your questions, and you have just performed rejection sampling. Right? Make sense, right?
Yeah.
Okay, sweet. Cool. The next part is exactly RLHF. You have performed supervised fine tuning, and now you want to make it helpful and harmless. And this is the Tiananmen Square massacre part. Everything they removed, you can do it through here. So wonderful. Finally, we have distillation. I am a bit over time, but I'll make it quick. The last thing that they did was find open source models that already exist and then perform fine tuning over that using the responses that the DeepSeek R1 gave. And they found that it did improve a lot of the reasoning performance, especially Llama 3.370 billion had a pretty significant jump in the performance after distillation. This is a mess. Okay, yeah. Here is the actual performance. Yeah. Llama, this is 3.3 specifically, improved pretty significantly. The only thing that they don't perform well is in programming related tasks. So I guess we don't have to worry too much just yet. They mentioned that they use supervised fine tuning and not reinforcement learning, but they said that they think reinforcement learning will perform better. I don't think this is exactly correct because they couldn't use reinforcement learning to fine tune the V3 base with the RL checkpointed dataset they obtained, but chose supervised fine tuning. So they are either very human or supervised fine tuning is in fact a very effective option, and reinforcement learning would not provide the gain compared to at least the cost of reinforcement learning. Cool. Then there are two things that didn't really work. One is process reward model, which again requires I think it requires a reward model, but the general idea over here is you want to reward not just the correctness of the answer, but also thinking about the answer the correct way, which again increases the amount of complications, requires you to evaluate intermediate step, and is challenging for general reasoning. Monte Carlo tree search is what AlphaZero used, but the problem with that is the state space that you have to search from is your vocabulary, and that is basically raised to the power of the actual sequence length that you are considering, which makes it incredibly expensive as well, so scaling becomes restrictive. That said, approaches do exist that combine the two and exhibit strong performance in specific specialized domains. So those are two papers that do combine those, and you can check them out if you like. Other drawbacks, one, reasoning-focused approach triggers some catastrophic forgetting, which is why they had to take 200,000 samples from their original data set for V3, and it also does perform poorly in tasks that are not represented strictly within the data set. So it does not generalize very effectively. It reasons in English, Chinese, even when the query language is neither. So if you ask it in French, it will choose to reason in English or Chinese. I presume the model has been trained for French, but this is some behavior that it just does not exhibit, so reasoning in the target language. And it doesn't work well with few-shot prompting. So just ask it the question, it will give you the answer, give it a couple of examples, and it does not work as well. And also doesn't work for 3 tasks, so thumbs up. Performance evals, it performs pretty impressively for most tasks. and that is just I don't know. It's a cool thing to look at, but I don't think much to discuss specifically because they do not include specific types of things that it failed at. It just gave us the final scores. Another graph over here also shows the performance relative to a bunch of additional data sets, and these are like MMLU, which is not specifically reasoning, simple QA, which is factual question answering, and again, performance is pretty representative, even in or actually, wait, is it not? It is not, right? Yeah, it is significantly worse than OpenAI's O1 in these set of tasks, except for IF eval, which I don't know what that is specifically referring to. So cool. That is all I had to present. Thank you very much for coming. Next week we will have NVIDIA Cosmos, which is also super interesting. So I look forward to seeing you all there as well. Extra pizza, please do.